Bismillahirrahmanirrahim. Assalamu alaikum. Today's topic is eigenvalues and eigenvectors of a matrix. This is very important topic, and since we are discussing the eigenvalues and eigenvectors of a matrix, and we already discussed in the previous lecture that the matrix basically represents a linear transformation. So in fact, we are also discussing side by side the eigenvalues and eigenvectors of a linear transformation here. So far we have done linear transformations, their images, pre-images, and matrices of these transformation. And again, this topic of today is mapped onto CLO2. And in today's lecture, we especially consider the square matrices, because the square matrices represent the transformation of same dimension into the same dimension. So in fact, we are talking about the linear operator, and the eigenvalues and eigenvectors are especially the properties that can be studied in a vector space, or in a single vector space. So we need a linear operator that maps the vector space onto it itself to study the problem of eigenvalues and eigenvectors. So suppose we have a linear transformation L, that is from Rn to Rn, defined by the matrix. So we have seen in the previous lecture that any finite dimensional vector spaces, and if we have a linear transformation on finite dimensional space, then it can be completely prescribed by the matrix of transformation. So suppose A is the matrix of transformation of L. So a natural question arises in our mind, and it is a question of considerable importance, that says x and ax belongs to the same space. Since after transforming the vector x onto the vector ax, this vector also belongs to the same space. This belongs to Rn, then this will also belongs to Rn. So what are the conditions, and when this is possible that these two vectors are parallel? So if we write this mathematically, then this is equivalent to that the effect of A on x will be the effect of an scalar when multiplied by x. That is, ax is equals to some lambda time x, where lambda is a real number or a scalar. So if this will be the case, then the effect of A on x will be the same as the scalar multiple of x. So it means then ax and x are the parallel vectors. So I can further explain this problem or this concept through this example. Suppose that we have a vector A and we have two vectors. Now, if we see here, if we apply this vector on x, then its image becomes 3, 6. So the image of this vector under A is the vector 3, 6. And the image of this vector under A is 5, 10. So if we draw these two vectors, then you can see very clearly that after transformation, this vector 1, 1 not only rotated, but also it is stretched and it becomes 3, 6. But if you see this vector 1, 2, then it is not rotated, but it is only stretched out. So this vector has some special property that after transforming A, after applying A on this vector, we obtain 5 times of the vector again. That is, the action of A on this vector is parallel to the vector 1, 2. Now there is a special name of this number 5 and this vector 1, 2. So what is this special name? Let A be an n cross n matrix. The real number lambda is called an eigenvalue of A if there exists a non-zero vector x in Rn such that Ax is equals to lambda x. So the 5 in the previous slide was the eigenvalue of the matrix A, and the vector 1, 2 was the eigenvector of the matrix A. So x is called the eigenvector associated with the eigenvalue of lambda. So it is very important to note that the eigenvectors always associated to an eigenvalue. So both of these concepts will occur together. So if we rewrite this equation, in this way, then here there is a matrix A of dimension n, and here there is a scalar. So we multiply this scalar with an identity of n, since if there is no operator, then there must be an identity operator, and we write this equation in the matrix form. So if we see this equation carefully, then you see that this is an n-dimensional homogeneous system, because this matrix is of dimension n and this is identity of dimension n, and if we simplify these two matrices, then we have a single matrix of dimension n, and so this system is the homogeneous system because right hand side is equals to 0, and we know that homogeneous system has always a trivial solution, and we always insist for a system which has a non-trivial solution. So for non-trivial solution, x must be non-zero, and so there is the condition on the vector x to be non-zero is a valid condition. So now another example, if you see that this is a matrix A and we need to find the action of A on this vector 1, 1, then we apply this matrix on the vector 1, 1, and we obtain 1 upon 2, 1 upon 2, and if we take 1 upon 2 as a common, then we obtain 1 upon 2 into 1, 1, which means that 1, 1 is the eigenvector of A corresponding to the eigenvalue 1 upon 2. Similarly, if we apply this matrix on the vector 1 minus 1, then we obtain here minus 1 upon 2, 1 upon 2, and if we take minus 1 upon 2 as a common, then we obtain 1 and minus 1, and this means that 1 minus 1 is the eigenvector of A associated with the eigenvalue minus 1 upon 2. So this matrix A has two eigenvalues. One is lambda 1, that is equal to 1 upon 2, and another is lambda 2, which is equals to minus 1 upon 2, and it has two eigenvectors corresponding to each eigenvalue. So if you again see this graph, then this is the vector 1, 1, and this is the vector 1 minus 1. Sorry, this blue vector is 1, 1. This blue vector is 1, 1, and this blue vector is minus 1, 1. And we multiplied this by 1 upon 2, then it shrinks to the half and it becomes 1 by 2 and 1 by 2. And similarly, this becomes we multiply this vector by minus 1 upon 2, so it shrunk also, and it reversed the direction, and it becomes minus 1 upon 2 and 1 upon 2. So this is the vector. So you see that the eigenvectors of a matrix do not change the line of action, their line of action. They can only stretch or compress or in the opposite direction or in the same direction, but they cannot be rotated or shifted their direction towards anything else. So this is the main property of eigenvectors. An eigenvalue determine the amount of their stretching or their compression. So if x is an this is also very interesting fact that if x is an eigenvector of A associated with the eigenvalue lambda, then every scalar multiple of x is also an eigenvector of A associated to lambda. Now you can see this property as that suppose x is the eigenvector of A, then Ax must be equal to lambda times x. Now, suppose that we apply A on a scalar multiple of x. Suppose k is a scalar. K belongs to R. So, if we apply this, then since A is a linear operator, so k can be written outside A. And we can write this by using the preservation of scalar multiplication. And since Ax is equals to lambda x, so it becomes k times lambda x. And since these two are both scalars, so they can be commuted and we can write it as k times x. So you can see here A times kx is equals to lambda times kx. What this means that kx is also an eigenvector corresponding to lambda. So what does this mean? This means that it is a one-dimensional space here, and every vector of that space is the eigenvector of A corresponding to the eigenvalue of lambda. And all of these eigenvectors are generated through this eigenvector x. So this space of eigenvector is called the eigenspace corresponding to lambda. And this is always there because whenever there is an eigenvalue and it has an associated eigenvector x, then that x always generates the space of eigenvectors. Those are eigenvectors corresponding to the eigenvalue lambda. Now another interesting fact that we impose the condition on the vector x to be non-zero, but the eigenvalues can be zero. For example, if we have a matrix A, then the action of matrix A on the vector 1, 0 is 0 times 1, 0. And this fact means that here lambda is equals to 0. So this is the eigenvector corresponding to the eigenvalue lambda is equals to 0. Now the next very important question, that how do we compute eigenvalues and eigenvectors? So for this, we have to see this equation, Ax minus lambda I x is equals to 0. So we cannot write x here and we take x as a common. So here A is 1 minus 2 and 1 4, a two-dimensional matrix. So there here I is also a two-dimensional identity. And if we write this here, then we get 1 1 minus 2 4 minus lambda 0 0 lambda times x is equals to 0. So this 0 is a two-dimensional vector, this x is also a two-dimensional vector, and if we subtract these two, then we get 1 minus lambda 1 minus 2 4 minus lambda times, let's say this x is equals to xy is equals to 0, 0. So this is a homogeneous system, a two-dimensional homogeneous system that I told you that the system would be an n-dimensional homogeneous system. So this is a homogeneous system, and we know that the homogeneous system has a non-trivial solution if this matrix is not invertible. So when if this is invertible, then we multiply by its inverse on both sides, and the answer would be xy is equals to 0. So there is only trivial solution. So for non-trivial solution, we must have a condition that this matrix is has inverse of this matrix does not exist. So the inverse of this matrix does not exist if the determinant of this matrix is 0. So we reach to the condition that this determinant, now I'm here, I had written the matrix, but here I am writing the determinant, that this determinant must be 0 for non-trivial solution. So what is this determinant is about? This determinant is basically the determinant of A minus lambda I matrix. So there is a very important name of this determinant. We call this determinant as characteristic polynomial. Why we call this determinant as polynomial? Because if we calculate this determinant, then we get 1 minus lambda, 4 minus lambda plus 2, and we get, I am solving only left hand side because I am talking about this determinant only and not this equation. So here, if we multiply and simplify these two factors, then we get here lambda squared minus 5 lambda plus 6. So we get a polynomial in lambda. So that is why this polynomial, this determinant is basically, whenever we calculate it, it is a polynomial in the variable lambda. And the degree of this polynomial is the dimension of the matrix. If there is a two-dimensional matrix, then there will be a polynomial of two dimension, and it has maximum two roots. So there will be maximum of two eigenvalues, and every eigenvalues have one eigenvectors, or depending upon the dimension of the matrix. So this is the theory is all about. So we call this as characteristic polynomial, and associated with this characteristic polynomial, we also call lambda as characteristic value. Eigenvalue is also called the characteristic value of A due to this characteristic polynomial. So to find the eigenvalues, we put characteristic polynomial is equals to 0. So if whenever now, from now onwards, whenever there is a square matrix and I say to you that put its characteristic polynomial is equals to 0, what will you do? You will write this determinant A minus lambda I of that matrix, and you put that is equals to 0. So you will obtain this characteristic equation. So the roots of this characteristic equation, since this is an equation, this is a polynomial, left hand side is a polynomial, and if we write is equal to 0, then this becomes equation, and it is called the characteristic equation. So the roots of this equation. The roots will be lambda 1 is equals to 2 and lambda 2 is equals to 3. These are the roots of this characteristic equation. So now we have the eigenvalues of this matrix. Now what we have to do, we need to find the eigenvector corresponding to these eigenvalues. Now to find the eigenvectors corresponding to these eigenvalues, what we need to do here. So we have a matrix, this matrix A minus lambda I matrix 1 minus lambda 1 minus 2 4 minus lambda. We have this system of equation x y is equals to 0 0, and we have find out the values of lambda for which this system has non-trivial solution. And what are those values of lambda? If these are values are lambda 1 is equals to 2 and lambda 2 is equals to 3. So we put lambda 1 is equals to 2 first, and then lambda 2 is equals to 3, and we calculate the eigenvectors one by one. So we first put lambda 1 is equals to 2 in this matrix, and we obtain minus 1, 1, minus 2, 2 times xy is equals to 0 0. So we obtain this system. And if we put lambda 2 is equals to 3, then we obtain the system 1 minus 3 is equals to minus 2, 1 minus 2, 4 minus 3 is 1 times xy is equals to 0 0. So if you write its augmented matrix to solve this system, minus 1 1 0 0 minus 2 2. This is the augmented matrix, and we put this augmented matrix into the echelon form after two operations. One operation is R1 transform onto minus R1, and second operation will be R2 is transformed into R2 plus 2R1. We obtain this matrix 1 minus 1 0 0 0 0. So the whole row is 0, and we know that such type of matrices represent that there is infinitely many solution of this system. So we know that there must be the infinitely many solution because we select the value of lambda so that this system has non-trivial solution. So if we write the solution of this system, then we are here x minus y is equals to 0, which means x is equals to y. So y is a free variable and x depends upon y. So if we take y is equals to some real number t, then we can write the solution vector x y as t t, and we can write it as t times 1 1, where t belonging to r. So this 1 1 is the eigenvector corresponding to the eigenvalue lambda is equals to 2. So the 1 1 is eigenvector corresponding to the eigenvalue lambda 1 is equals to 2. And if we write this eigenvector as this, so this generates the whole space, If we write it like this, then this is the eigenspace. So every vector in this space is the eigenvector corresponding to lambda 1, and we take only the generator of this space and we say that this is the basically eigenvector, and every scalar multiple of this vector is also the eigenvector. Similarly, you can calculate the eigenvector corresponding to lambda 2 is equals to 3. So this is your exercise to calculate the eigenvector corresponding to lambda 2 is equals to 3. Now, all of these things that we explained in the previous slide, I summarize it like this. Let A be an n cross n matrix. Then determinant of A minus lambda I is called the characteristic polynomial of matrix A. And so the eigenvalues are also called the characteristic values of a matrix A. This polynomial is of degree n, as we have seen in the previous slide. We solve the characteristic equation determinant of A minus lambda is equals to 0 to find the eigenvalues of A. And so the eigenvalues are basically the roots of characteristic polynomial. Then we solve this system for every eigenvalue to find its corresponding eigenvector. As we did here, we solve this system. For each of its eigenvalue, there are two eigenvalues, so we solved it twice to obtain all the eigenvectors corresponding to every eigenvalues. And this system is an n-dimensional system with coefficient matrix A minus lambda I. We see that this is a two-dimensional system with the coefficient matrix of A minus lambda I. So this is the summary of how do we compute the eigenvalues and eigenvectors of the system. Now there is another example of a three-dimensional matrix. So first we need to find its eigenvalues and eigenvectors. So we find its eigenvalues and eigenvectors. So we write its characteristic polynomial first. So its characteristic polynomial will be determinant of A minus lambda I. Now here A is of dimension 3, so this identity will also be of dimension 3. I write it directly. How? Because this matrix has only diagonal entries and it has lambda on its diagonal entries. So we deduct lambda from the diagonal entries of this matrix A and we write the characteristic polynomial as 1 minus lambda, 2 minus 1, 1 minus lambda, 1, 4 minus 4, 5 minus lambda is equals to 0. So this is the characteristic equation of this matrix. So if you expand this determinant, then you will obtain the characteristic equation or polynomial equation as lambda cube minus 6 lambda square plus 11 lambda minus 6 is equals to 0. So this is a cubic equation, and you know the roots of the cubic equation can be determined by this constant term. If the coefficient of this term is 1, then the factor of this term can be the root of this equation, may be the root. So for initial guess, we can write that maybe the roots of this equation may be plus minus 1 or plus minus 2 or plus minus 3 or plus minus 6, because all of these are factors of 6. So we first try 1. So when we put 1 in this equation, let's say, so we get 1 minus 6 plus 11 minus 6. So it becomes 12 minus 12 and it is equals to 0. So luckily we have the root, that is lambda is equals to 1 is the root of this equation. So we determine here that lambda is equals to 1 is the root. Now by synthetic division, we obtain the other root. So synthetic division, I repeat it here. So we write here the coefficients of these lambdas power 1 minus 6, 11 minus 6, and we write the root, that is 1 here, and we copy this one here, we multiply this one with 1 and we add it. So here is minus 5. Then we multiply this minus 5 with 1 and again we add it and we get here 6, and we multiply 1 with 6, then we obtain 0. So here again it is checked or verified that lambda is equal to 1 is the root, because the remainder becomes 0. So we can write this polynomial as lambda minus 1, that is this root lambda is equal to 1, and the rest of the root, this is the coefficient of lambda square, this is the coefficient of lambda, and this is the coefficient of lambda power 0. So we write is lambda square minus 5 lambda plus 6 is equals to 0. So if we factorize this, then we have 3 eigenvalues: lambda minus 1, lambda minus 2, lambda minus 3 is equals to 0. Since this is a matrix of 3 dimensions, so it has at most 3 eigenvalues. Lambda 1 is equals to 1, lambda 2 is equals to 2, and lambda 3 is equals to 3. So to find the eigenvector corresponding to these 3 eigenvalues, we need to solve this system 3 times. One time for lambda is equals to 1, one time for lambda is equals to 2, and one time for lambda is equals to 3, to determine all the eigenvectors corresponding to all the eigenvalues. So I am doing this exercise for lambda is equal to 1, and it is your exercise to complete this problem to find the eigenvectors of lambda is equals to 2 and lambda is equals to 3. So for lambda is equals to 1, we write this matrix A minus lambda I x is equals to 0. So this matrix becomes 1 minus 1, 2 minus 1, 1 minus 1, 1, 4 minus 4, 5 minus 1, x1, x2, x3, or you can write x, y, z as you like. So this is the system. So if we write its augmented matrix, then the augmented matrix becomes 0, 2, minus 1, 1 minus 1, 1, 4 minus 4, 4. Or this is the augmented column 0, 0, 0. So this is the augmented matrix. And if we solve it, we solve it to find the solution to be minus 1 upon 2t, 1 upon 2t, and t, where t belongs to R. Again, this is a one-dimensional space, and this is space generated by this vector minus 1 upon 2, 1 upon 2, and 1. So this is the eigenvector corresponding to lambda 1 is equals to 1. And you can also multiply this vector by 2, let's say, to remove, if you want to remove this fraction, then you can also say that if you multiply this vector by 2 and you say that minus 1, 1, and 2 is the eigenvector. So maybe you say that this is the eigenvector, or I say that no, this is the eigenvector, but as far as both are the linear multiple of each other, then we both claim, our both of the claims are right. And if we write this in the set, then this set becomes a eigenspace. One-dimensional space with the generator, this vector. Now your exercise is to find the eigenvectors like this by using lambda 2 is equals to 2 and lambda 3 is equals to 3 in this matrix. Now, in this slide, we will see that how physically these eigenvectors can be visualized. So suppose we have this space, and this space I have mentioned here two vectors. This vector is x1 and this vector is x2. So these are the two vectors. So now carefully note the directions of these two vectors. Now if we apply the action of a transformation on this space by twisting this space, or you say rotating this space. So what will be the action of that rotation on these vectors? So we rotate this space, and you see if we rotate here, then see carefully the x1 vector, that this x1 vector changes its direction. Before it is like this straight, and now it becomes that vector. But if you carefully see the vector x2, it stretches but it does not change its line of action. So in this example, it is clear that this x1 is not the eigenvector, and because it deforms when I apply the force, but this vector x2 is the eigenvector of this space. Now if we again do the same exercise and we twist in the opposite direction, then we see the same experience. So this is the physical or real life example of the linear transformation. This concept of linear transformation uses when these modern cars are designed, and this concept of eigenvectors is used when designing the axle of the cars, the shocks of the cars, so that the jumps or the noise outside would not come inside the car, and the car comfort will be maintained at any cost. So another application related to the same application, it is the stretching of an elastic membrane. Suppose we have elastic membrane in xy plane whose boundary is the unit circle, x square plus y square is equals to 1. Now this membrane is stretched, and the transformation matrix is applied, is given by this matrix A. So that if we apply this matrix on any vector xy transformed into the vector 5x plus 3y and 3x plus 5y. Now suppose we want to know the directions which are not deformed under this stretching. That is, we want to know the direction which are either stretched or compressed but do not rotate after the application of this stretching. So these directions are also called the principal directions. And in fact, what are these principal directions? These are simply the eigenvectors of this space under of this matrix. So this is a very simple problem. Again, we write the characteristic polynomial of this a minus lambda I is equals to 0, which is equals to 5 minus lambda 3. 3, 5 minus lambda is equals to 0, and this becomes 5 minus lambda whole square minus 9 is equals to 0, and if you solve it, you will obtain lambda 1 is equals to 2 and lambda 2 is equals to 8. So after simplification. So you can simplify it here. It will become lambda square minus 10 lambda plus 16 is equals to 0. So these are the two roots. Now for lambda 1 is equals to 2. Lambda 1 is equals to 2. Now lambda 1 is equals to 2. We find 5 minus 2, 3. 3, 5 minus 2 times x1, x2 is equals to 0, 0. So if you solve this system, then you will obtain the eigenvector as 1 minus 1 corresponding to lambda 1 is equals to 2, and you will find the eigenvector 1 1 corresponding to lambda 2 is equals to 8. So 1 1 1 1 is somewhere here, so this direction, and 1 minus 1 would be this direction. So basically these are the directions which remains unaltered when we stretch the elastic membrane, and all the other directions will be deformed. So that's all from this lecture. Thank you very much for your attention.